I want to talk briefly about doing math with integers. And you might ask why? Like, why not just use a float or a double and just have as much precision as you want, and not worry about integer rounding and truncation? Basic reason is that lots of cheap, low-power processors don't have floating point units. Even today in 2020, you can still find small, cheap, low-power processors that don't have built-in hardware to do floating point math, and instead emulate it in software. And so if you use integer math, you can have performance that's much, much faster, 50, 100 times faster than trying to do floating point math. You might say, well, but I'm going to do math on, on a big computer, or I'm going to do it on some other more expensive piece of hardware. So that's not my problem. Even in that case, oftentimes doing integer math instead of floating point math can sometimes be faster, and it is almost always more energy efficient. So if you're doing, for example, neural network computations, if you can find ways to do that with fixed point math, with integers, or treating those integers as having a fixed number of decimal places, you can oftentimes get speed ups or major power savings versus doing things in floating point. So keeping that in the back of your mind is always helpful. Okay, so here's a little example. We've got a program that's going to take one input value, x, and it's going to run from 0 through 100, incrementing each time. And we want to, for each value of x, we want to multiply it by 2.5. And we've got this reference value that we're going to do with floating point operations, but we want to replicate that basic multiplication by 2.5 with an integer computation. So eliminate multiplying here by 2.5 as a floating point number, and just do the same thing with integers. And then here in the print statement, we're going to print x and y, and then print what the reference should be, if it did the calculation without any errors. And if there is any error, the difference here will print out. Okay, so there are good ways and there are bad ways to do this. So for example, we could write x, y equals x times 5 over 2. Because 5 over 2 should give us 2.5, and then just multiply x by that. Okay, so then we can go ahead and just compile this program. So see integer math.c. And then we can run it. Okay, and as we do this, already you can see that there's some pretty big errors here accumulating. So if we go up to the beginning, if x is 0, x times 2.5 is still 0. That works out all right. But if x is 10, for example, 10 times 2.5 should give us 25. But instead we get 20. And if you look at every value of y, we're just multiplying by 2. So if x is 15, y gets 30 instead of 37. So what's happening here? Well, 5 is being divided by 2 first because we put the parentheses there. So 5 divided by 2 is 2.5. But because that's an integer operation, the half gets dropped. It's truncated, and so we just have 2. So in this overall computation, we're just saying x times 2, which is not at all what we were trying to do. Okay, well, what could we do that's better? We could reorder some of these operations. So we could say like x divided by 2 times 5. Right, and that would give us, again, mathematically it's equivalent. So let's try it and see how we do here. Okay, so now we see that we've at least reduced the huge error that we had here. But we still get some errors some of the time. So let's go back. So for example, for 10, this works out correctly. We get no error. So if x is 10, then x divided by 2 is 5 times 5 would be 25, and that's the correct answer. But if x is 11, we still get 25. So x divided by 2, 11 divided by 2 would be 5.5. And again, that half is getting dropped. So then this still ends up evaluating to 5. We multiply by 5 and we get 25 when we really wanted to get 27. So what can we do? Well, in this case, if we just rearrange these, so let's multiply first and then divide. So we'll multiply, x times 5 divided by 2. So with order of operations, it'll do this left to right, but we could put parentheses to make that more clear. So if we do the multiplication first and then the division, then we minimize any loss of precision. The only thing we have to be careful about is that we don't overflow the integer. So if we were dealing with really big numbers, we might need to be concerned about that. And we should put in appropriate checks if we're taking user input of any kind to make sure that we're not going to overflow. But if we do this again, we see that there's no error now. So, for example, we could take 11 multiplied by 5 would give us 55, and then dividing 55 by 2 would give us 27.5, and we drop that remaining fraction, and that gives us 27 like we would expect. So sometimes thinking about integer math is a little bit tricky. You have to think about what each of the steps are, and is there some ordering of the steps that are better than others. Sometimes if you do have to be careful not to overflow, you might multiply by something and then divide by something else, and then multiply again and divide by another factor, just to make sure you don't overflow. This is actually like a whole field of study, and there are special tools to help you optimize this kind of computation if you ever really need to, if you're implementing this on a low power processor or doing digital signal processing on an FPGA. But for right now, just a little bit of careful thought should be sufficient.